Hey guys, in today's video we'll be covering Unit 2.8 of the Math AA, SL, and HL course, which is rational functions. So first we'll start with the self-inverse function. And first let's have a function, right? So we have this function here, f of x equals 1 over x. And now that we have this function, we want to find the inverse. So the inverse of f of x. And you know that to find the inverse, you just switch the places of the x and the y and solve for y, right? So if your original is y equals 1 over x, your inverse is x equals 1 over y. And then you just solve for y, so you have x times y equals 1, y equals 1 over x. So here you just multiply both sides by y, times y, and then you just divide both sides by x. And here you finally end up with the inverse is 1 over x, right? And now if you notice, the original function and the inverse function are the same. So here you have f of x equals the inverse function. And whenever you get this case here, whenever f of x equals the inverse, this is called a self-inverse function. So this here is your self-inverse. Okay, it's just a concept that you have to be familiar with. Self-inverse is when f of x equals the inverse function. Okay, so next we'll move on to our reciprocal functions. And for this, we'll just have a normal function first, so f of x, and we'll make this 2x minus 2, for example. Okay, so let's graph this function here. Let's draw a graph. And so your x-intercept, first of all, x-intercept is when y equals 0, right? So 2x minus 2 equals 0. And we'll just solve for x, so 2x equals 2, x equals 1. So this is your x-intercept. And your y-intercept is when x equals 0. So 2 times 0 minus 2 equals your y-intercept. And then you just, the x's cancel out and you have minus 2 equals y. So your y-intercept is at minus 2. And we just draw a line going through these, and this is your function of x here. This is your f of x. Okay, so what is the reciprocal function? This function here, your original function, this can be rewritten as 2x minus 2 over 1, right? Because it's divided by 1, it'll give you the same thing. And your reciprocal function is essentially when you just switch these two around. So you make the denominator into the numerator and the numerator into the denominator. So our reciprocal function, we'll call it r of x, r for reciprocal, and this will be 1 over 2x minus 2. This is your reciprocal function here. And why don't we graph this? Let's draw a graph of this. So first step is to find the x asymptote, right? And as we said in unit 2.4, your x asymptote is basically what x can never be. And you know that when you have a fraction here, you can never divide a number by 0. So this bottom here, 2x minus 2, can never be 0. And you just solve for x, so 2x can never be 2, x can never be 1. So here you already have an x asymptote, at x equals 1. And now let's find our y asymptote. So your y asymptote is, and for this we're going to assume that this numerator here is always a constant, so there's never any x's up here. If there are x's, we'll get to that later in the video, but for now we'll just assume it's always 1 or 2 or whatever. Okay, and you know that to find the y asymptote, you just make x a really big number, so the function of a really big number, right? And you will have 1 over whatever minus 2. Okay, this really big number, minus 2. And you know that when you divide a number or divide 1 by a really big number, you will get an answer that's really close to 0, but it's not 0, right? It's just really close. So let's say you have like 0.00001 or something. And the bigger you go, so the bigger than x, the smaller the number you'll get, but it will never actually touch 0, which is why you have an y asymptote at y equals 0. And let us actually label this x asymptote here, so x cannot be 0, and the y asymptote, y cannot be 0, right? So since y will never be 0, we know that there's going to be no x-intercepts. But let's find the y-intercept of this reciprocal function. And for the y-intercept, if we make x equal to 0, you'll have function of 0 equals 1 over 2 times 0 minus 2, which is minus a half. So the graph intercepts the reciprocal intercepts the graph at a half over here. And now we have this. We can determine that the graph is in the first and third quadrant. We'll get to that later. But we just draw the graph here. We just connect the dots. And you'll notice our graph looks something like this, right? And what relationship can we see between the original graph and the reciprocal graph? And so the main relationships which we got, I'll just paste them on screen now. First of all, the x-intercept of f of x is the x-asymptote of the reciprocal. And I already established that here, right? So the x-intercept here is the x-asymptote of the reciprocal, right? Here, reciprocal asymptote. Next, we have that assuming that the numerator is always a constant, assuming there's no x's up here, then the y-asymptote of the reciprocal will always be 0, always run through the 0 line here. And since there's no values when y equals 0, this means that there's going to be no x-intercepts. So r of x has no x-intercepts. Again, this is assuming that there's no variables up here. It's always a constant. And finally, the y-intercept of the reciprocal is 1 over the y-intercept of the normal function. So the y-intercept of a normal function here was minus 2, right? And the y-intercept of a reciprocal is minus a half, which is minus 1 over 2. If this was, let's say, 4, this would be 1 over 4. If this was 1,000, this would be 1 over 1,000, and on and on. And yeah, this is your reciprocal function. Again, this is assuming that the numerator is a constant. It has no variables. And now we move on to rational functions, which are functions in the form of, for now, ax plus c over bx plus d. All right, so it's basically, for now, we're only going to be looking at two linear functions on top of each other. If you are doing SL, this is as far as you're going to go with rational functions. If you're doing an HL in 2.13, you're going to see quadratics and cubics and other types of higher powers of x in these rational functions. But for now, we're only going to have two linear functions on top of each other. And when we said in reciprocals, the top is always 1, here it's not 1 anymore. Here it's a linear function. So what differences are we going to see now? First, let's look for the x asymptote, right? And x asymptote. And x asymptote, as we know, is when the bottom equals 0, because you can't divide by 0. So bx plus d cannot be 0, right? And you can just rearrange this, so bx cannot be minus d, and x cannot be minus d over b. And this is the general rule, which will work for all rational functions, which are two linears on top of each other, and it's that the asymptote is minus d over b. You don't have to memorize this because it's really easy to derive, and you can just work it out by yourself in a question, but this is the general rule. And now we move on to the y asymptote. And if you remember, for reciprocal functions, we said the y asymptote is always 0, but now that's not going to be the case. And why is that? Well, we know that the y asymptote is when you have a function of a really big number, right? So let's say a function of 10,000. You put it in for the x and you have 10,000a, sorry, this is a 0, plus c over 10,000b plus d, right? And now this plus C, this plus D, they become so insignificant that we can kind of just ignore them for now. Like they don't really make that much of a difference. And you're gonna have 10,000 A over 10,000 B. And we kind of just cross these out because they're the same. And you're left with A over B. Now, your graph is never going to touch the value of A over B. It will get really, really close to touching it, but it will never actually touch it, right? Which is why it's an asymptote. So the y-asymptote is A over B. And now you have your x-intercept. And for reciprocal functions, we didn't have an x-intercept because the graph never touched y equals 0. It never touched the x-axis. But now the asymptote is not at y equals 0. It's going to be somewhere else. So we will have an x-intercept. And how do we find this number? Well, x-intercept is when y equals 0, right? So when ax plus c over bx plus d equal to 0. And this bx plus d, we just multiply both sides, it cancels out. You have ax plus c equals 0. And then you just solve for x, and you're left with x equals minus c over a. So minus c over a. And finally, we have our y-intercept. And our y-intercept is when x is 0, so the function of 0. And this will be a times 0 plus c over b times 0 plus d, right? And this a times 0 is 0, b times 0 is 0, and you're left with c over d. So your y-intercept is c over d. And as you can see, this is really simple. These four rules, kind of, that every two linear functions on top of each other are going to follow. You don't have to memorize these, of course. It's just an understanding of how you do it. Pretty simple, not much to do. If you're HL, it does get a bit more spicy, but for now, this is all you have to know. And now we'll finish off this video with a past paper question, where you're asked to graph the function of f of x equals 3x over x minus 2, showing any asymptotes at intersections. So let's do the asymptotes first. So our x asymptote, right, is when the denominator equals 0. So when x minus 2 equals 0. And we just move the 2 across and we have x, or cannot be 0, so x cannot be 2. Just draw a dotted line here where x cannot be 2. Next we have our y asymptote. And we can do the whole make x a really big number, whatever. Or we can just use the rule we learned last time, which is that the y asymptote is a over b. And in this case, a is 3, b is 1. So our y asymptote is 3 over 1, which is just 3. So here, let's draw a dotted line, and y cannot be 3. And next, let's do our intercepts. So let's use orange here. So our x-intercept, right, is when y equals 0. So it's when 3x over x minus 2 equals 0. And you just bring the x minus 2 across, and you have 3x equals 0, x equals 0, right? And if we do our y-intercept now, so our y-intercept is when x equals 0, so the function of 0. And this will be 3 times 0 over 0 minus 2, which is 0, right? So the line crosses the graphs at 0, 0. So the 0, 0 here is our intersect. And now we can draw our graph. So we know it stays within these two lines, touches here, and then goes back down. And since there's one in the third quadrant, there has to be one in the first quadrant too. So there's going to be one here that is symmetrical across. And yeah,